Introduction: the new geometry of motion. The automobile has long been defined by its limitations. For over a century, we have accepted that a car must be a static object when parked, a prisoner to its turning circle when maneuvering, and a victim to the elements when the sky turns grey. We have designed our cities, our garages, and our daily routines around these mechanical constraints. But what if the vehicle was no longer a rigid box? What if it could respond, adapt, and transform? Optimise Technologies, Automobile Blueprints is a journey into a near future where engineering serves intuition. This book, authored by Tim R., explores a radical rethink of vehicular architecture. We move away from the one-size-fits-all mentality of traditional manufacturing and toward a philosophy of kinetic optimization. Within these chapters, you will find blueprints for a new breed of machine. Vehicles that deploy protective armor against hailstorms. Chassis that breathe with inbuilt wind turbines to harvest energy while they rest. Wheels that rotate 90 degrees to erase the frustration of urban parking. Interiors that maintain a sanctuary of purity through automated decontamination systems. This is not just a book about cars, it is a blueprint for the next evolution of human mob, safer, more sustainable, and infinitely more exhilarating. Welcome to the future of the road, ILT. It is an exploration of how smart materials, autonomous systems, and creative mechanical design can converge to create a driving experience that is. Let us begin the optimization. 1. The kinetic shield, revolutionizing vehicular resilience. The image of a car cowering under a concrete overpass during a sudden hailstorm is a familiar one. It represents a fundamental vulnerability in modern transport. Our most expensive daily assets are often at the mercy of the sky. However, the emergence of active roof-mounted shielding arms marks a transition from passive endurance to active defense. This chapter explores the engineering philosophy and multifaceted benefits of a deployable kinetic mechanism designed to safeguard a vehicle's most critical vulnerabilities during extreme meteorological events. 1. The geometry of protection. A vehicle's Achilles heels are undoubtedly its glass surfaces and horizontal body panels. During a severe hail event, ice stones, often traveling at terminal velocities exceeding 100 km per hour, can shatter tempered glass and leave dimple patterns on aluminium hoods that are nearly impossible to repair without full panel replacement. An automated roof-mounted mechanism provides three primary structural advantages. The air gap cushion. Unlike a soft car cover, a rigid mechanical shield creates a buffer zone between the impactor, hail, and the vehicle surface. This allows the shield to absorb the kinetic energy E equals 21 MV2 and dissipate it through the roof rack mounts rather than the fragile glass. Deflection angles. By deploying at an incline as seen in the forward sloping plates, the mechanism changes the angle of incidence. Instead of a direct perpendicular hit, hailstones glance off the surface, significantly reducing the force of impact. Comprehensive coverage. A well-engineered system protects the windshield, rear window, and panoramic sunroofs, which are the most expensive and structurally vital components to replace. 2. Stability in high-velocity winds. While hail causes visible trauma, high winds present a hidden structural threat. A common concern with car covers or stationary shields is the sail effect, where the wind catches the device and flips the vehicle or tears the mechanism off. Modern kinetic shields address this through aerodynamic neutrality. Pressure equalization. Slotted panels or breather gaps allow air to flow through the mechanism, preventing a low-pressure vacuum from lifting the car. Active counterweighting. Advanced systems use sensors to detect wind direction, tilting the plates to act as a spoiler, effectively using the wind zone force to press the car more firmly into the pavement downforce. 3. Economic and psychological peace of mind. Beyond the physics of impact, the benefits of a deployable roof mechanism extend into the realm of logistics and finance. Benefit category. Impact of active shielding. Insurance premiums. Potential for active safety discounts, similar to anti-theft or dashcam incentives. Resale value. Prevents the salvage title status that often follows a total loss hail claim. Operational continuity. Eliminates the 2 to 4 week waiting period at body shops following a regional storm. 2. The autonomous valet, mobilizing high-density event parking. Urban density and the surge in large-scale public gatherings have created a critical bottleneck, the parking deficit. Traditional parking infrastructure is static, expensive to build, and often underutilized outside of peak events. The emergence of the autonomous mobile parking system, AMPS, often referred to as a parking bus or mobile car carrier, offers a dynamic solution. This system can be leased to councils and event organizers to temporarily double parking capacity in space-constrained environments. 1. Mechanism and engineering, doubling the footprint. The AMPS utilizes a combination of omnidirectional robotic carriers and multi-level palletless stacking technology to maximize vertical and horizontal space. Cooperative robotic transport. 2 or 4 modular mobile robots slide under a vehicle, clamping and lifting the wheels through a double slider mechanism. These robots work in tandem to transport cars without requiring the driver to be present. Aisle-free dense parking. Because the robots are omnidirectional, they can move vehicles into incredibly tight configurations. By eliminating the need for traditional driveways, ramps, and door-opening gaps between cars, the system can increase parking capacity by up to 60% within the same surface area. Vertical stacking modules. The bus unit acts as a mobile docking station, deploying hydraulic lifts that allow cars to be stacked 2 or 3 levels high. This mobile car stacker model turns a flat 100-car lot into a 200-car facility within hours of deployment. 2. Operational leasing, a plug-and-play solution. The primary value proposition for local councils and concert organizers is the parking as a service (PaaS) model. Rather than investing in permanent concrete structures, they can lease the amps for specific durations. Council utility. Councils can deploy units to congested central business districts during holiday periods or street festivals to mitigate traffic overflow and illegal parking. Event and concert logistics. For stadiums or remote festival grounds, amps units provide a temporary surge in capacity, reducing the time attendees spend circling the block and improving overall traffic flow. Ease of installation. Surface-mounted systems do not require deep excavation or pits, making them ideal for temporary use on existing parking lots or reinforced green spaces. 3. Revenue generation and economic sustainability. Beyond space optimization, the AMP serves as a powerful revenue-generating asset for its lessees. Revenue stream. Description. Dynamic pricing. AI-driven software adjusts rates in real time based on occupancy levels and event peak times, e.g., higher rates 1 hour before a concert. Premium valet fees. Users pay a premium for autonomous valet services, where they drop the car at an entrance bay and the system handles the rest. Operational savings. Automation reduces the need for on-site wardens and parking attendants, significantly lowering labor costs. Increased throughput. Faster retrieval times via smart software, often under 2 minutes, allow for higher vehicle turnover throughout the day. 3. The Panoramic pilot. Transparency is the ultimate driving interface. For decades, the automotive industry has focused on adding digital displays to the cabin to enhance the driver's perspective. However, the next frontier in immersive travel is not a better screen, but the removal of visual barriers entirely. This chapter explores the concept of the transparent cockpit, a vehicle designed with a see-through front end and structural glass integration to provide a visceral, exhilarating connection to the road. 1. The design philosophy, immersive velocity. Traditional car design creates a tunnel vision effect, where the driver is separated from the pavement by a massive engine bay and an opaque dashboard. The concept featured in our architectural studies reimagines the vehicle's front as a continuous, high-strength transparent arc. Visual continuity. By extending the windshield down to the front bumper line, the driver gains a direct line of sight to the road directly beneath their feet. The flying sensation. At high speeds, this transparency creates an illusion of gliding just inches above the asphalt, transforming a routine drive into a high-definition sensory experience. Aesthetic integration. The see-through front isn't just a window, it reveals the precision engineering of the suspension and steering components, turning the car's nervous system into a design element. 2. Engineering the invisible. Material and safety. A transparent front end introduces unique structural challenges. Traditional steel crumple zones must be replaced with materials that offer both clarity and extreme impact resistance. Polycarbonate ceramic composites. The front fascia utilizes advanced transparent ceramics that provide the hardness of glass but the impact resistance of high-grade polymers, capable of withstanding high-velocity road debris. Structural glass A-pillars. To maintain a panoramic view without sacrificing rollover protection, the pillars are engineered from reinforced transparent aluminum or high-strength layered glass, ensuring the roof remains stable under pressure. Heat and glare management. A see-through front would typically lead to greenhouse heating. The concept utilizes electrochromic tinting, which automatically darkens based on sun intensity, and infrared reflecting coatings to keep the cabin cool. 3. Safety procedures and redundancies. Operating a vehicle with such a radical field of view requires new safety protocols to prevent driver distraction and ensure structural integrity. Distraction filtering. While the view is exhilarating, it can be overwhelming. The system includes an augmented reality (AR) overlay that highlights hazards, potholes, pedestrians in the transparent field, ensuring the driver's focus remains on safety rather than just the scenery. Impact retraction. In the event of an unavoidable collision, the internal seat mounts are designed to tilt backward slightly, while the transparent front panels are engineered to shatter into rounded, non-lethal granules. Cleaning and maintenance. For a see-through car, a single smudge can be a safety hazard. The vehicle employs a high-pressure air blade system and hydrophobic nanocoatings to instantly repel rain, mud, and dust without the need for traditional wipers. 4. The future of human-centric design. The transparent cockpit moves the car from a box of utility to a tool of perception. It is particularly valuable for performance driving, allowing drivers to see the exact positioning of their front tires relative to the apex of a curve. Sightseeing and tourism, providing passengers in scenic areas with a 180-degree vertical view of the environment. Conclusion: the transparent front end is a bold step toward the dematerialization of the automobile. By prioritizing the driver's visual connection to the world, we create a vehicle that doesn't just transport the body, but engages the mind in a constant, exhilarating dialogue with the road. 4. The Aeolian Charger, harnessing stationary wind for EV autonomy. For years, the dream of wind-powered cars was dismissed as a violation of the laws of thermodynamics, primarily because mounting turbines to capture wind while driving creates parasitic drag that consumes more energy than it generates. However, a new paradigm has emerged: static wind harvesting. This technology focuses on the 95% of a vehicle's life spent parked, transforming the car from a passive consumer into an active energy producer during its downtime. 1. The retractable turbine system. The core of this concept is a series of inbuilt vertical axis wind turbines (VAWTs) seamlessly integrated into the vehicle's upper chassis or roofline. Unlike horizontal turbines, VAWTs are proficient at capturing wind from any direction without needing a complex aiming mechanism. Integrated protective covers. While the vehicle is in motion, the turbines are recessed and sealed behind aerodynamic, flush-mounted panels. This ensures the car maintains a low coefficient of drag (CD) to preserve driving range. Electronic deployment. Upon parking, the vehicle's central computer evaluates the local wind conditions. If thresholds are met, the protective covers slide open, and the turbines telescope upward to engage the ambient airflow. 2. Intelligent activation, sensors and automation. The system is designed for set-and-forget operation, utilizing a suite of smart sensors to manage energy harvesting. Air movement sensors, ultrasonic anemometers constantly monitor ambient wind speed and turbulence. The turbines are only activated when wind speeds exceed a cut-in threshold, typically around 3 to 5 meters per second, ensuring mechanical wear is only incurred when meaningful energy can be captured. Geofenced suitable places. The car's GPS can identify high-yield wind zones, such as coastal parking lots, ridgetop viewpoints, or open event fields. When parked in these geofenced areas, the system automatically prompts the driver to enable Aeolian mode. Safety overrides. The system includes a rapid retraction protocol. If sensors detect extreme wind gusts that could damage the turbine blades or destabilize the vehicle, the units are immediately stowed and locked. 3. Energy contribution and grid independence. While a small vehicle-mounted turbine cannot fully recharge a long-range battery in a single afternoon, its contribution to auxiliary sustainability is significant. Feature: performance impact. Energy generation can produce between 50 W to 400 W depending on turbine size and wind velocity. System maintenance. Powers always-on systems like Sentry cameras, cabin climate preconditioning, and battery thermal management. Range extension. Over a 24-hour park period in a windy area, the system can recover 5 to 10 miles of range, often enough for a daily commute. 5. The threshold of purity. Advanced footwear decontamination systems. For the connoisseur of luxury automobiles, the interior is more than a cabin, it is a curated sanctuary of fine leathers, bespoke wool carpets, and hand-finished veneers. The greatest threat to this pristine environment is the outside world, brought in on the soles of footwear. This chapter introduces the Threshold Purity System (TPS), an automated shoe cleaning tray integrated into the vehicle's rocker panel, designed specifically for those who view cabin cleanliness as an extension of their personal discipline. 1. Mechanical sophistication. The Kinetic brushing array. The core of the TPS is an automated, retractable tray that deploys from the side sill upon the opening of the door. Unlike static floor mats, this system utilizes active mechanical cleaning to ensure zero transfer of debris into the vehicle. Counter-rotating bristle brushes. The tray features high-density, soft polymer bristles that rotate in opposing directions. This action gently but thoroughly dislodges mud, grit, and organic matter from the intricate patterns of a designer shoe's sole. Precision torque sensors. To protect delicate footwear materials, such as suede or soft calfskin, the brushes are equipped with sensors that adjust the rotation speed and pressure based on the resistance encountered, ensuring a deep clean without abrasion. Recessed deployment. When the door is closed, the entire assembly retracts into a sealed, self-cleaning compartment beneath the door sill, maintaining the vehicle's aerodynamic profile and aesthetic lines. 2. The integrated atmospheric shield. High-velocity dust extraction. Removing physical debris is only half of the challenge. Fine dust particles often remain airborne or loosely attached to the upper surfaces of the shoe. The TPS addresses this through a dual-stage air management system. Positive pressure blow fans, integrated into the perimeter of the tray. High-velocity fans create a localized air curtain. This pressurized air stream pushes dust and microscopic particles away from the interior door gap and back toward the exterior environment. Acoustic damping. Given its application in luxury vehicles, the blowers utilize soundproof seals and silent drive motors to ensure the cleaning process does not disturb the serene silence of the cabin. Static neutralization. The airflow system can be infused with ionizing technology to neutralize the static charge on dust particles, preventing them from clinging to the car's carpets or leather surfaces upon entry. 3. Safety and user protocol. Integrating a mechanical cleaning system into a vehicle's entry point requires stringent safety procedures to protect both the passenger and the vehicle's electronics. Safety feature. Function. Pinch point detection. Infrared sensors immediately halt brush rotation if a finger or loose garment is detected near the mechanism. Obstacle avoidance. The tray will not deploy if the vehicle's proximity sensors detect a high curb or nearby obstacle that could damage the unit. Automated drainage. A dedicated internal channel ensures that any water or mud removed from shoes is drained out the bottom of the chassis, rather than accumulating in the tray. 6. The protective cocoon. Engineering transit safety. The journey from the factory floor to a customer's driveway is arguably the most vulnerable period in a vehicle's lifespan. Despite the heavy machinery and logistics involved, the final few miles of delivery often pose the greatest risk for minor cosmetic defects, the dreaded lot rash, door dings, and stone chips. To combat this, the industry has evolved from simple plastic wraps to the advanced safe travel cushion (STC) systems seen today. 1. The anatomy of an external buffer. Modern delivery cushions are not merely pieces of foam, they are multi-layered protective systems designed to balance impact absorption with paint-safe adhesion. As shown in the provided images, these systems typically consist of impact deflecting shell, a durable, weather-resistant outer layer, often reinforced polymer or high-density nylon, designed to take the brunt of a strike from car doors, shopping carts, or loading straps. Compression core. The internal cushion uses high-density memory foam or air pocket technology to dissipate kinetic energy. Soft touch backing, a non-abrasive microfiber or silicone-based interior lining that prevents the cushion itself from scratching the vehicle's clear coat during movement. 2. Strategic placement for maximum defense. Protection is only effective if it covers the vehicle's high-strike zones. When a new car is prepped for transit, cushions are applied to 4 critical areas. Zone. Vulnerability. Protective solution. The quarter panels. Wide-set areas prone to sideswiping in tight trailers. Extended vertical cushions, as seen in the BMW example, that span the wheel arch to the mid-door. Door midsection. Direct impact from neighboring vehicles during loading, unloading. Horizontal impact strips positioned at the widest point of the door frame. The leading edge. Debris and kickback from the transport truck's tires. Contoured nose guards that wrap around the front fascia and headlights. Wheel arches. Curb rash or contact with tie-down chains. Specialized circular or semicircular guards that shield the rim and fender lip. 7. The modular urbanite, redefining accessibility and safety in low-speed transit. As urban centers become more congested and theme parks expand into sprawling micro-cities, the demand for a new class of vehicle has emerged, the low-speed, high-accessibility electric shuttle. This vehicle is engineered specifically for environments where the maximum speed is strictly capped at 40 km per hour, prioritizing safety, ease of use, and continuous operation through innovative energy management. 1. Safety through speed limitation and stability. By capping the maximum velocity at 40 km per hour, the vehicle inherently reduces the kinetic energy involved in potential maneuvers, making it ideal for high pedestrian areas like city centers or resort grounds. Collision mitigation. At these lower speeds, the risk of severe impact is drastically minimized, allowing for a lighter chassis design that focuses on occupant comfort rather than heavy-duty high-speed crash structures. Thermal management. The 40 km per hour limit ensures that the electric motors and batteries are never subjected to high drain, high heat scenarios. This significantly reduces the risk of thermal runaway or combustion, ensuring the vehicle remains safe even in crowded environments. 2. The swap-and-go battery architecture. The defining feature of this vehicle is its externally accessible battery system located at the front and sides of the chassis. This swap-and-go methodology eliminates the range anxiety and downtime typically associated with electric vehicles. Continuous operation. One battery pack can remain at a designated charging station while the vehicle is in use. When the onboard power runs low, the driver simply swaps the depleted unit for a fresh one, a process designed to be as simple as changing a household battery. Front-mounted accessibility. Placing the batteries in external, easily reachable compartments ensures that users do not need specialized mechanical tools or a lift to manage the vehicle's power source. Combustion prevention. The external mounting provides natural air cooling and ensures that, in the unlikely event of a battery fault, the power source is isolated from the main cabin, allowing for immediate and safe removal. 3. Ideal use cases. This vehicle is not intended for the highway, it is a precision tool for the last mile and controlled environments. Environment. Primary benefit. Theme parks. Silent, zero-emission transport for guests between attractions with easy overnight fleet battery swapping. City centers. Navigating narrow streets where traditional cars are bulky and high speeds are dangerous. Corporate, university campuses. A reliable shuttle for students and employees that can run 24/7 by rotating batteries between shifts. 4. Accessibility and inclusion. The upright, boxy design is more than an aesthetic choice, it maximizes interior volume relative to the vehicle's footprint. Large glass panels provide 360-degree visibility, crucial for navigating around pedestrians, while the low floor height ensures that stepping in and out is effortless for elderly passengers or those with limited mobility. 8. The gracious leap, the art of the automotive hurdle. In the realm of theoretical transport, we often focus on efficiency, safety, and torque. But what if we prioritize the survival of a confused squirrel over the laws of physics? Enter the gracious leap protocol, an abstract, highly impractical, yet deeply empathetic concept for the modern road farer. This isn't about transportation, it's about a momentary, airborne act of kindness. 1. The hop detection array. In this hypothetical scenario, the vehicle is equipped with a suite of sensors. Unlike standard LiDAR, which sees an obstacle as a hazard, these sensors identify souls. The fauna filter, a specialized algorithm that distinguishes between a stationary cardboard box and a panicked deer. The anticipatory pulse. Seconds before contact, the car calculates the leap trajectory, ensuring the jump is high enough to clear the animal but low enough to avoid low-hanging traffic lights. 2. Mechanics are the mechanical pogo. Since traditional tires are built for rolling, the leap protocol requires a total suspension mutiny. Pneumatic sudden expansion (PSE). Upon detection, the suspension struts act like high-powered pogo sticks, venting a massive burst of compressed air to launch the chassis upward. The mid-air shimmy. To maintain balance, the wheels rotate 90 degrees mid-jump, borrowing from the lateral leap architecture, acting as gyroscopic stabilizers to keep the car level while the animal passes safely underneath. 3. The passenger experience. The Uber. Humorously, the biggest challenge isn't the jump itself, but the interior physics. The gravitational gulp. For the passengers, the experience is akin to a sudden elevated drop, followed by a moment of weightlessness. The T-stabilizer, cup holders. A mandatory feature for this vehicle would be gimbal-mounted cup holders to ensure that while the car is jumping a badger, your morning latte remains perfectly level. 4. A hypothetical scenario, the midnight possum. Imagine a straight, moonlit highway. A possum freezes in the headlights. In a standard car, this is a tragedy. In the gracious leap vehicle. Detection. The fauna filter chirps a polite animal ahead. Notification. The launch. The car's front end lifts with a soft whoosh, followed by the rear. For 1.5 seconds, the vehicle is a 2-ton projectile of mercy. The underpass. The possum looks up to see a matte black underbelly passing 3 feet above its head. The landing. The car touches down with the grace of a cat, or perhaps more realistically, a very heavy sofa, and continues at a steady 40 km/h as if nothing happened. 9. The sun catches of Solara. The gravel crunched beneath the tires of the Aurelius EV as Elias pulled into the center of the salt flats. Here, miles from the nearest charging station and deep within the high desert basin, the silence was absolute. He checked the dash, 12% battery remaining. In a standard electric vehicle, this would be the onset of range anxiety. In the Aurelius, it was simply the start of the afternoon shift. Elias reached for the center console and tapped a sapphire blue icon labeled Solar Deploy. The architecture of the wings. With a soft, mechanical hum that sounded like a long-drawn exhale, the roof of the car transformed. This wasn't the clunky, rigid solar integration of the early 2020s. This was kinetic origami. 4 primary struts, finished in matte carbon fiber, rose from the roof rails. As they ascended, they unfurled a series of ultra-lightweight, high-efficiency monocrystalline panels. To an observer, it looked less like a machine and more like a giant silver hawk stretching its wings after a long sleep. The panels didn't just lay flat, they tilted, tracking the trajectory of the sun with surgical precision. Within 60 seconds, the Aurelius had tripled its surface area, casting a wide shadow over the parched earth below. Harnessing the heavens. The technology behind the wingspan system was a marriage of aerospace engineering and silicon chemistry. Gallium arsenide cells. Unlike domestic rooftop panels, these utilized multi-junction cells capable of pulling energy from across the light spectrum, including the infrared heat shimmering off the salt flats. The stationary advantage: by only deploying when the car was parked, the designers avoided the aerodynamic drag and weight penalties that had killed previous solar car concepts. Thermal regulation: as the panels soaked up the sun, a liquid cooling loop beneath the cells pumped heat away, preventing the cabin from becoming an oven and ensuring the battery stayed in its Goldilocks temperature zone. The slow charge: Elias leaned his seat back, watching the energy flow visualization on the heads-up display. Current intake: 3.2 kilowatts. Estimated range gain: 18 miles per hour. Status: optimal solar alignment. It wasn't a lightning-fast supercharge, but it was free. It was silent. It was a bridge between the kinetic energy of travel and the static energy of the cosmos. For the next 4 hours, while Elias read his book and watched the shadows of the mountains lengthen, the sun would pour nearly 70 miles of range back into the floorboards of the car. In the old days, being stuck in the middle of nowhere was a tragedy. With the Aurelius, the middle of nowhere was exactly where you wanted to be. The car wasn't just a vehicle anymore, it was a self-sustaining island in a sea of light. 10. The Guardian's glow. The intersection at 5th and Main was a chaotic symphony of city life, pulsing with the rhythm of heavy foot traffic and the quiet hum of electric motors. In the past, this was a place of high-stakes guesswork. Pedestrians would peer through tinted windshields, trying to lock eyes with drivers to discern their intent. Was the car slowing down to turn? Was it maintaining speed to go straight? Then came the Aegis signaling system. The language of light. As Marcus approached the zebra-striped crosswalk, a sleek, matte silver sedan glided toward the intersection. In the center of its front fascia, a sharp, amber chevron pulsed into existence. This wasn't a standard headlight or a decorative trim piece. It was a dynamic intent indicator. The symbol, a bold, upward-pointing arrow, was the car's way of speaking to the humans in its path. The straight path protocol: the system was linked directly to the car's navigation and steering rack sensors. When the onboard AI confirmed the vehicle was maintaining a straight course through an intersection, the amber chevron activated. Pedestrian priority: the glow was specifically calibrated to a wavelength that cut through rain, fog, and the glare of city neon, ensuring that even a distracted commuter could see it in their peripheral vision. Non-verbal safety: for the elderly or the hearing impaired, who couldn't rely on the sound of an engine to judge a car's momentum, the symbol provided a definitive go, or stay, visual cue. The psychology of predictability: the genius of the Aegis symbol lay in its simplicity. By removing the ambiguity of a driver's intent, the technology reduced the micro-hesitations that often led to accidents at busy crossings. When Marcus saw the amber arrow, he knew the car wouldn't be making a sudden right hook into his path. The sedan wasn't just a machine following a lane, it was an active participant in the safety of the street. It was a handshake between silicon and soul, engineering the intent. Beneath the hood, the technology was more complex than a simple light bulb. Predictive analytics: the car used LiDAR and computer vision to identify the zebra path 50 meters before arrival. Pedestrian detection: if the car sensed a person stepping off the curb, the chevron would pulse at a faster frequency, acknowledging the pedestrian's presence, essentially saying, "I see you, and I am continuing straight." Cross-network sync: in smart city hubs, the car's amber symbol synced with the intersection's own traffic sensors, creating a safety corridor of light that guided pedestrians across the asphalt. As the sedan crossed the intersection, the chevron dimmed and disappeared back into the car's seamless frame. The ambiguity of the road was vanishing, replaced by a new, glowing vocabulary of safety. 11. The cruise on the coast. The Great Ocean Road is traditionally a driver's masterpiece, a winding, narrow ribbon of asphalt clinging to the limestone cliffs of Victoria. But for Leo, reclining in the Orbis 7, the road was no longer a task to be managed. It was a gallery. As the autonomous chassis hummed southward toward the 12 Apostles, Leo didn't stare through a fixed windshield. Instead, he felt the subtle, buttery rotation of the Omnipod. While the car's wheelbase maintained its unwavering path along the centerline, the entire glass-domed cabin began a slow, clockwise drift. The engineering of the gimbal drive. The Orbis 7 was built on a radical premise: why should the passenger be a slave to the direction of the wheels? The car's architecture was split into two distinct entities. The skateboard chassis, a flat, heavy base containing the solid-state batteries and 4 independent steering motors. This layer handled the boring physics of staying on the road. The maglev turntable, the round cabin sat atop a high-powered electromagnetic ring. This allowed the pod to rotate with zero mechanical friction, meaning the passengers felt no grinding or vibration as they turned. The horizon lock algorithm, at low speeds, specifically designed for scenic tours, the car's external cameras identified landmarks like the Razorback Rock Formation. The cabin would then automatically pivot to keep that landmark perfectly centered in the passenger's field of view, regardless of how the road twisted. The U-turn paradox. The most striking feature of the Orbis 7 was its dismissal of traditional geometry. As Leo reached the end of the Bay of Islands, he decided he wanted to see the sunset from a different angle back the way he came. In a conventional car, this would involve a three-point turn on a dangerously narrow shoulder. In the Orbis, Leo simply spoke to the AI, reverse course. The chassis didn't move. Instead, the cabin performed a seamless 180-degree rotation. What was once the front of his seat was now the back. The car's control software simply reassigned the drive motors, the rear wheels became the front wheels, and the Orbis began driving in the opposite direction without ever having to turn its nose. In the world of the Orbis, forward was a state of mind, not a fixed point on a compass. A 360-degree social space. Inside the pod, the engineering allowed for a lifestyle shift. Feature, function, panoramic persistence. The cabin can rotate 360 degrees to follow the sun, keeping the interior naturally lit or shaded as desired. The 0G step. When parked, the cabin rotates its door toward the safest exit point curbside, deploying a set of illuminated stairs. Centrifugal dampening. Even if the cabin rotates quickly, internal gyroscopes adjust the seat pitch so the passenger never feels dizzy. 12. The kinetic idle, powering the extra mile. The red light at the intersection felt eternal, the kind of stillness that usually breeds frustration in the modern commuter. For Jax, however, the stop was an invitation. As the vehicle's sensors confirmed a complete halt, the Volta Kinetic hub emitted a soft chime, and the center of the steering wheel decoupled with a tactile snick. The engineering of the extra mile. While the energy generation of a single person is modest, roughly 50 to 100 watts, the Volta system was designed to bridge the gap between stranded and safe. In the world of high-efficiency EVs, every joule counts. The range buffer, the energy generated during a 3-minute traffic light, doesn't power the massive drive motors. Instead, it feeds the low-voltage auxiliary battery. By manually powering the car's computers, sensors, and interior lights, Jax was saving the main high-voltage pack for pure propulsion. Supercapacitor bridge. The hub is connected to a small supercapacitor that can dump its charge instantly. If the car's main battery hits 0%, a vigorous minute of panic cranking can provide enough emergency burst to move the car several hundred feet, often the exact distance needed to reach a charging stall or clear a dangerous lane. Efficiency multiplier. The car's AI calculates the human energy offset. For every watt Jax generates, the car adjusts its climate control and battery cooling more aggressively, effectively extending the total range by a small but vital percentage over a long journey. The distress mechanism, tactile flow. The true genius of the Volta was that it turned energy production into a therapeutic experience. The system utilized magnetorheological fluid (MRF) inside the hub to transform the act of spinning into a sensory anchor. Adaptive tension. Using internal biometric sensors, the wheel detected Jax's heart rate. If he was stressed, the wheel increased its resistance, requiring a slow, rhythmic push that encouraged deep, regulated breathing. Haptic heartbeat. As the hub spun, it produced a subtle vibration against the palms, a simulated pulse that synced with the car's ambient lighting to induce a state of flow. Sensory textures. The inner ring featured micro-textures, from cool, smooth ceramic to a warm, grained wood, giving Jax a sensory anchor during the wait. Mood status. Harmonizing manual contribution. 45W auxiliary load fully covered, Zen level, peak. Jax settled into the rhythm. He wasn't just killing time while the car sat idle. He was a micro-generator, a human turbine reclaiming his own focus while feeding the machine. By the time the light turned green and the magnetic locks snapped the wheel back into its rigid driving configuration, Jax was refreshed, and his car had gained the extra mile of peace of mind. 13. The evolution of roadside assistance, integrated automated lifting systems. The traditional scissor jack, a staple of vehicle emergency kits for decades, is often cited by drivers as one of the most stressful and physically demanding tools to operate. From finding the correct pinch weld to the manual exertion required to lift a 2-ton vehicle, the process is ripe for modernization. This chapter explores the emergence of integrated automated car raisers, designed to transform tire changes from a grueling chore into a seamless, push-button operation. Engineering a hands-free lift. The concept of an automated hoist relies on a shift from external tools to vehicle-integrated hardware. By embedding the lifting mechanism directly into the vehicle's chassis or suspension assembly, the system eliminates the search and set phase of a tire change. As seen in current prototypes, these systems generally utilize 2 primary designs. Chassis-mounted outriggers, retractable arms that extend from the underbody to the ground, providing a stable base and lifting the frame directly. Suspension-integrated actuators, robotic arms mounted near the wheel hub that can push off the ground, lifting the specific corner of the car while keeping the wheel assembly accessible. 2. Comparative efficiency, manual versus automated. The primary advantage of an automated system is the drastic reduction in the time to lift. Feature traditional jack automated integrated system. Setup time 3 to 5 minutes, locating jack points, less than 30 seconds, software deployment. Physical effort high, manual cranking, pumping minimal, in-cabin or app control. Stability variable, dependent on ground level, high, self-leveling sensors. Safety high, risk of slippage low. 3. Technical components of the system. To achieve the precision required to lift a vehicle safely, the system incorporates several high-tech modules. Robotic articulated arms. These arms use multi-jointed segments to adapt to uneven terrain, ensuring the base remains flat on the pavement even if the car is on a slight incline. Hydraulic or electric actuators. High-torque motors provide the muscle needed to lift significant weight without requiring external power from the user. Sensor feedback loop. Integrated pressure sensors detect when the base has made solid contact with the ground, preventing overextension or tilting. IV. Safety considerations and redundancy. Lifting a vehicle remains a high-stakes operation. Automated systems must address potential failure points. Mechanical locks. Once the desired height is reached, mechanical pins engage to ensure the car cannot drop even if the hydraulic or electric system fails. Ground surface detection. Systems are designed to abort the lift if the ground is too soft, e.g., mud or loose gravel, to prevent the hoist from sinking or tipping. Proximity sensors. To prevent injury, the system can detect if a person or object is under the vehicle before initiating the descent. Design insight. Modern prototypes focus on a stilted approach, where the lifting arm connects to the reinforced suspension or frame members to ensure the vehicle's structural integrity is maintained during the lift. V. The future of roadside self-sufficiency. As vehicles become increasingly autonomous, the physical maintenance of those vehicles must follow suit. The integrated hoist represents a move toward a self-servicing vehicle architecture.